Welcome guys to the P102.2 lecture. In this lecture we are going to initiate with where we have closed in the last lecture. In the last lecture we have gone through the dimensional analysis, and similarly I'm going to do one more example to deepen your knowledge on dimensional analysis. So in this example what we are going to do is that we are going to look at a pendulum to see if we can calculate the relation using dimensional analysis itself. Let's find out an equation. How could it be related? How the oscillations of a pendulum is related? So you have some dimensions here. Now the first dimension is the mass of the pendulum. The second dimension is its angle with which you are swinging the pendulum, right? So the next dimension is the length of the pendulum string. And then you have the other dimension, which is the acceleration due to gravity, again, which is acting as a force keeping these pendulums bob down to the ground. That is also there. Now, I'm going to, there's a time, okay, there's a time as a dimension, okay. So there's a time for this pendulum to get here and get back to here, and then turn it all the way back to this place. That means that's the time period of oscillation, the time taken for this pendulum to move around from here to here. That's the time period. So let's write down the dimension of time again. Okay, so the time must be related to all these factors. Let's see which of these factors are related using only dimensional analysis. That's the point of this example. So let's keep some function of theta. It would be some function of theta, L, M, and then there is other thing. Okay, there's gravitational acceleration, right? So it could be that. So we can write down that T must be proportional to the dimensions of theta is in radians, so it has no dimension, and L, which is length, so it has the dimensions of the length, and mass has the dimensions of mass, and G has the dimensions of L by T squared, right? T squared. So that's the dimension of G. Okay, so I don't know how this is related. I only know that t raised to 1 is our solution. For these values we can put down alpha, beta, gamma, and okay, let's put down, as I already told you that the theta is in radians, so it has no implication, direct implication. It will be a function, it will be a constant. So let's write down that this has alpha, beta, and gamma. Okay, so that's the relation right there. Now as you know, we have a t in this side and there's a t downstairs, so you can say that t raised to 1, so you can say that minus 2 gamma, because it's in the downside, so it's minus 2 gamma must be equal to 1. So you can say that gamma is equal to minus 1 by 2. Okay, and similarly there is no L dependence on the left side. That means alpha is equal to, okay, there is L dependence, there is 2L, 2 L's here, L raised to alpha and L raised to gamma. So alpha plus gamma must be equal to 0. That means we already know gamma, the value of gamma. So we can put it that back here, and you can write down alpha, or alpha is equal to 1 by 2, right? 1 by 2. So we got that as well. Now we got alpha, gamma, and the only thing is m has beta, so there is no beta term in the left side. That means beta is equal to 0. So that's it. Our solution will comprise of some constant, which will be a term of theta times uh, alpha raised to 1 by 2, that's L raised to 1 by 2, right? So that's L raised to 1 by 2 times L by T square, that's G raised to minus 1 by 2. Okay, that was very close, I'm sorry about that. So you can write down that T will be some function, will be equal to some function, say y of theta. It will depend on theta, and because if the amplitude is higher, then the time will be larger, right? It's like going from this far to this far and this far to this far, so the time will be substantially higher if you have a longer distance to cover, right? So you can say that for short theta values, we'll see that this is common logic, but we will see something else in our observations. But it is only applicable to theta being smaller than, say, 20 degrees. Okay, so it will be a function of theta anyway, times L raised to 1 by 2, so it's square root of L by G, right? So that's the equation of time period. Okay, in the future when we do this problem using physical principles rather than dimensional analysis, we will find that it will be 2 pi root L by G. So you can see how correlated and correct our intuition was by just using dimensional analysis. So with that, let's go to other one more little topic. Okay, that topic is called Avogadro number. Gadro, Avogadro numbers. Okay, so Avogadro number. So the Avogadro number is is something that you see in daily life. You have a material like this. Okay, you have material like this. It comprises of atoms, and atoms itself will make molecules. So atoms becomes molecules, and these molecules will make up for the whole of any material that you see around the world. So how can you understand the principle in within the crystal, or the material? Okay, in within the material, if you zoom in, okay, zoom in, and you can see that these atoms are having some kind of a bonds in between. Okay, these bonds can make certain shapes. If the shapes are uniform and they form a pattern, these patterns repeat itself to make up for the whole of the atom, so it will cover the whole of the atom. Such patterns, okay, if there is such pattern, that kind of a material is called crystal and crystalline materials. Okay, and if the material is made up of tiny particles, tiny molecules that are not repeating itself but so random that when you look at from one point, you see the same every direction, the same in every direction. It's almost uniform, there is no pattern which repeats itself. Then that kind of a material is called amorphous. Okay, so these two kind of materials are there. You will see, you have already learned this in basic chemistry and physics as well. So in this crystal, you can classify the crystal as comprising of lattice. Okay, these lattices make up for the whole of the material. So in lattice points, there are points in lattice where the molecules are located, okay, where the atoms are located. So atoms and molecules will form some kind of a bond to create a crystal lattice. Okay, in this lattice, okay, there could be a large number of molecules forming bonds in between them. That's the shape of the lattice. Okay, this shape repeat itself and form the most part of the crystal. Okay, that's how crystal is. If this is the shape, it will repeat itself. So if we take out a single part of a crystal, that is a lattice, you can see that the atoms number of atoms inside, number of atoms. So these crystal can be comprising of different kind of materials, okay, depending upon the characteristics of the material. So Avogadro number is called something of a ratio of number of total atoms divided by number of moles. Okay, that's a basic representation. If there is, this means that it states that it is the number of moles. Now the weight of one mole of a material is called Avogadro number. Okay, it's actually the weight of one mole of material. So it's a molecular weight of one mole of material. If you take one mole of material, that's what effectively it means. So you have a total number of atoms and you have the number of moles. That means it's the ratio of what is inside one mole. Okay, so you can say that uh, the amount of substance, the number of substance inside one mole of an atom, or a molecule, or a mole, not an atom but a mole, will be 6.2 into 10 raised to something into 10 raised to 28, right? So that's a universal constant that Avogadro introduced. So with that as well, I'm going to end this lecture right here.